So there will be 3 tests, and they will cover 3 areas that we'll be talking about. And I will introduce these areas later on. And you need to have a positive grade out of each of these tests. So these are requirements. The lectures, I will be recording them, and I will be putting these lectures somewhere so that they will be available to you. So I will be sending you links to these lectures. Also the slides will be posted online. I will set up a group for this subject, for this course on VCamp. So on VCamp, hopefully by our next meeting, there will be a group, maybe earlier, and this will be probably the basic channel of exchanging information. The lectures, I don't know what is your preference in terms of timing. I don't know whether you prefer this lecture to begin at 3:15, or should we rather begin at 3? Both are available. So if you could just type in the chat box, let's make some small poll, which is better. If there is a conflict, because if someone has a conflict, ends at 3 some other class, then it might be difficult. Okay, so I guess that we agreed. I hope it's convenient to all of you. And we'll be beginning at 3, so that means the lecture would last by 4:30. Today's lecture will be longer, 15 minutes longer. I don't know whether there is anything that you would like to know at the very beginning of our meeting, our first meeting. What probably I missed some message. Maybe you want to know some other organizational thing that could be of interest to you. If not, during a lecture you can interrupt, or maybe at the end of the lecture you can be back with organizational questions. Okay, so if there are no questions, let's begin the lecture. At the end of this first introductory set of slides, I will show you some tentative course plan. And I will be trying to make this introduction as short as it is possible, because we don't have much time assigned to the course, and the course is quite extensive. Because probably the subject is becoming quite important. So we will be talking about fundamentals of artificial intelligence. I would like to begin with the history of artificial intelligence, and there is a quotation that I put here on this slide, which is quite symbolic to the field. This has been said by Hall. Hall was I don't know whether you were watching a movie that named 2001 Space Odyssey. This is a very interesting movie. This is a science fiction movie. So the movie is 2001 Space Odyssey. And the movie is quite interesting because it has been shot in 60s. And it is quite important and quite symbolic for artificial intelligence because the screenplay, the script for this movie was written by researchers, or with an quite important contribution from the leading researchers in the field. And it is interesting because they were trying to make prediction how this artificial intelligence would look like in 50 years, or a little bit less than 50 years, from the point they were in. I recommend to watch it, and this is a quotation. These are words that were said by Hal. Hal was a computer, and it was a vision on what the computers, how far they can get in almost 50 years from that point in time. And it was intelligent computer. Interesting thing from watching this movie is that that you can see what has not been predicted at all, and where the authors overshoot. So, for example, the authors were not realizing that we will be using extensively graphical user interfaces. So most of the communication between crew and the computer is done using keyboards and a screen. On the other hand, the computer was able to fluently recognize speech, was able to synthesize speech. So for the standards of technology in 2001, that was overshoot, because we were not able to understand speech, continuous speech, and synthesize speech that time. But now we can. So this is something I recommend. If you have a minute, just try to download this and watch it, because it is interesting to know how people envisaged development of artificial intelligence that time. So this brief history, I will just take a while. It began together with computers. So artificial intelligence as a science, as a research, originated at the moment where computers were developed. Computers were developed for the purpose mainly of code breaking. These were code breaking machines to speed up and to enable the decryption of secret messages. And in 50s and 60s, when people were developing this computer technology, they realized that since they are based on logic, because the operation of a computer binary system is a direct correspondence to logic, they thought that suddenly we have a tool that can implement any logical expression or any logical reasoning, so that we can create an intelligent entity. And as it usually happens at the beginning of development of every new field in research, there was an extreme excitement, and there were great expectations. So this is also quite interesting that because one of the nicknames for this period was a sentence or an expression, "Lukma, no hands." People were trying, were hoping that there will be a very rapid development in capabilities of these computing machines, intelligent capabilities. And this was not obviously so simple. And the more they were studying the field, the more obstacles emerged. And in 70s and 80s, there was a almost complete closure in financing of artificial intelligence, just because people realized that what can be done using the technology they had and using the theory they had was able to solve only trivial problems. There was this time was a time where it was virtually impossible to get any funds for AI research. And right now we are in the next or the third phase of development of artificial intelligence, where it just entered markets and entered our everyday life. Because of few very important theoretical advancements and due to technological breakthroughs that has been that occurred in recent years. So these advancements are manufacturing more capable, more powerful hardware. And the second thing, which is extremely important, is that everything is now wired, is online, is within a reach of internet. So we can communicate from any place with any other place if only we have paid for this possibility. So we'll be talking about artificial intelligence. So it is good to think for a while, what is intelligence? And basically intelligence is a notion that is with us as long as humankind is on the earth. But there are no very precise or sufficiently precise definitions of intelligence. And since they are imprecise, they cannot be a good basis for doing research. So if we would like to make artificial intelligence or intelligent machines, we need definitions that are more concrete and so that they can be form a basis for rigorous research efforts. So at the beginning of work on artificial intelligence, there were three different directions have been established. So I put them as constructive definitions of artificial intelligence that somehow are identifying objectives and tools that can be used for evaluating whether research has been completed correctly or incorrectly. So the first definition was that AI systems are systems that cannot be distinguished from humans. Basically, this definition focuses on the outcome of operation of algorithms that we'll be trying to develop. And it just says how to test whether an algorithm can be considered intelligent or not. And this means for testing is a Turing test. A Turing test is a test that assumes that there is a person and is communicating with an entity using means that are that cannot provide you with clues on whether this entity is a human or whether this entity is an algorithm or a machine. And the purpose of this test is to make assessment whether we think that this is a machine or not. So if this setup assumes kind of conversational contact with this entity, and we are asked that within some specified period of time, we are asked to make a decision whether we think this is a machine or not. I will comment on it a little bit more a little bit later. So the second definition is completely different. That says that AI systems are systems that process information like humans. This means that we are trying to make AI by trying to clone or copy what we know about our neural systems. So this approach is implemented in the field of research that is called artificial neural networks. And at the basis of this research is a research on how neural networks operate, what is their architecture, what is a basic processing element of nervous systems, both human, but in principle, all living creatures have similar hardware for processing information, and we are trying to understand how it operates. And the last definition was a definition that says that AI systems are systems that think and act rationally. And basically, that was probably the first way of developing AI algorithms. The first direction, they assumed that we will be trying to build algorithms that are mathematically correct or logically correct, that can be proved that all reasonings that we are making are justified, and logic is a basis of this direction of AI development. So these three, let me just a little bit elaborate on these three different definitions and directions of research that they imply. So this Turing test definition is focused on evaluation methodology, and it is basically addressing ability of the algorithm to understand natural language and to use this natural language. So that's why NLP, or natural language processing, here is the focus of scientific efforts. And as you know, right now it is becoming quite common that you meet systems that implement results of this research track. There is a multitude of different chatbots available on the internet. If you write down a chatbot or chatterbot into your browser, you'll find several different sites that offer you opportunity to test different algorithms or different solutions using this Turing test. You can engage in conversations, and sometimes you will be surprised how interesting such conversations can be. So some of these algorithms are really good. And the other example of implementation of these ideas are present in growing number of virtual assistants that are developed by different companies to substitute a need to employ help desk workers. So in many big companies have already developed different automatic assistance so that you can try to solve your problem without engaging human into the picture. Also, virtual assistants are available in different computer operating systems. You have virtual assistants for Android. Unfortunately, this is, since at the core of this technology lies natural language processing, all these solutions that has been developed, they were developed mainly for English-speaking world, maybe Chinese-speaking world, Spanish-speaking world, not necessarily in Poland. They do not necessarily operate in Poland. But you have, for Microsoft, you have Siri, which is such an assistant. For I'm sorry, Cortana and Siri you have for iPhones and iOS. The second direction in AI research is probably right now the dominant one. And these are these neural networks. And these neural networks are responsible for breakthroughs in AI. And AI has become competitive to humans right now. And it can successfully accomplish different, very difficult tasks, like recognition of information that is embedded in n-dimensional data, like in images or in texts. So you can get very reliable detectors of different objects, different types of objects, visual objects, person detectors, car detectors, or pedestrian detectors. You can also get different solutions that classify texts according to their contents, for example. Also, we have recognition of information embedded in sequences of vectors. Like we can recognize actions in video. We can recognize speech. We can translate speech. We can convert text to speech, speech to text, and so forth. Neural networks also help us or enable generation of data. You have virtual actors. You have the whole right now flourishing domain of fake industry, fake images, fake videos. So all of these solutions are provided by different neural architectures. Just briefly, because we'll be talking about neural networks, just briefly, it began in around 2014, so it's relatively short time from the moment where these neural networks became really competitive to humans. And one of the first tasks that were solved by neural networks in a way that is better than for humans was recognition of road signs. And the task was here, the network was compared to humans in a very realistic setup. So the sign has been presented for a limited amount of time, just like in reality. So you are seeing a sign for 10 seconds and you are asked to tell what was that. And in using this 2014 architectures for the problem, which involves 40 different categories, and the network was trained, because we are training networks. I will comment on it later. It appeared that neural networks were beating us actually 10 times. We were making 4% errors, networks 0.4% errors. And soon there a variety of other image object recognition tasks were performed. So, for example, the next step was recognizing objects that are more difficult than road signs, natural objects. So here there was a database that is called ImageNet. So there is an ImageNet, is a huge repository of different images. And so 100 categories have been selected from this ImageNet repository, hundreds of thousands of different examples, and the network was trained and then confronted with human ability to recognize objects. And here are simple sample examples from operation of this system. So on the left, you have here is a challenge. So the trained network has been presented with this image, and what was after processing of this image, the network was producing 5 most likely candidates as a response. So as you can see, the winning hypothesis out of 5, the most likely hypothesis, the most likely was that this is a container ship. Here on the right, again, the network was right and was pointing to a motor scooter. And again, on this task, it appeared that networks are better than us. The network is not making no errors. It makes errors. Here are 2 examples of erroneous responses of a network. So in the first case, for example, this picture, according to a label, presents cherries, and the network says this is a Dalmatian. So most likely we could also make this kind of a mistake. So if it mistakes, it mistakes in a way that is acceptable. Here is another example. Here the network made a mistake because it has never known about the Madagascar cat, which is, I presume, some species of monkeys. The network was doing its job not that poorly, because it knew about squirrel monkeys and spider monkeys, which I have never heard of. So if I am asked the question, what is this? Probably it's impossible that I will provide a right answer. Neural networks are, the research on neural networks is exploding right now. So they can all not only perform tasks where we have a very specific and exact framework for this task completion, where we exactly can specify what is right, what is wrong. But also they have enormous capabilities of being, let's say, creative. So one of the very also, I think, well-known applications of neural networks is in something that is called artistic style transfer. So the whole point is that we have a network, this algorithm. We first try to train this network to understand and use some particular artistic style And the artistic style here that is being used is a style of different famous painters. So the objective of the experiments was, for example, to repaint the picture that you see in the upper right corner using different artistic styles that were learned by a network. So the first style that was learned by a neural network was Van Gogh style. That means that the network was being presented with samples of Van Gogh's paintings. And it learned to apply this style and to convert this picture. So here on the left, you have this Van Gogh style. On the right, you have a different style. This is a Munch. This is another painter, which was it had a completely different way of painting. As you see, it's an extremely creative way of behavior. So neural networks are extremely capable. I'm sorry. So this is where I should get. And just to conclude these three different definitions and these three different directions in research, I'm back to this logic. And this logic was the basis of early development in artificial intelligence. And it is still present in particular tasks. And not only logic is used, there is something that are called search algorithms that are also quite commonly used right now. There is a variant of logic that is called fuzzy logic that is also used. So these are three different basic directions in artificial intelligence right now. A symbol of a success of AI right now, or maybe not right now, year or 2 years ago, were autonomous cars. So autonomous cars were equipped with systems that had to cope with different kinds of intelligent tasks. The first task was recognition. So if I want this car to safely travel, it needs to see, it needs to hear, and it needs to know where is it. And that means it needs to recognize first visual scenes, recognize audio, what is going on in this audio channel, and it needs to localize itself. So it needs to recognize where is this particular, where it is in a particular moment of time. Next, it has to make predictions. It needs to understand that if you would like to take an action, these actions need to be taken appropriately so that you can get to a goal, a desired goal. So it involves predicting what will happen if an action will be executed and how the world will change if the action gets executed. Next, there is a planning. Before I can make or execute an action, I need to plan this action. I need to learn how to use my actuators to actually execute the action. And obviously, I need to learn. I need to learn because a programmer is unlikely to give me all the answers to a fast-changing and unpredictable environment. And all these actions can be implemented basically with neural networks alone. But typically, the tools that are used right now for performing each of these intelligent behaviors for recognition, neural networks are the winners. I mean, there is no competitor right now to neural networks in recognition. Also, there is no competitor in prediction. In planning, neural networks, or something that is called reinforcement learning neural networks, are competing with search algorithms. Both are used in practice. And in case of control of all different actuators that are necessary, if we are talking about an autonomous devices, machines, here neural networks compete with fuzzy logic. And I put this slide just to emphasize that we will be having three different research directions or concepts or strategies that we will be covering during this course. So we'll be talking about neural networks. So this is a neural network, so forgive me. So we'll be talking about neural networks. We'll be talking about search algorithms. So this is the second family of methods, and we'll be talking about fuzzy logic. So this will be the contents of this course. And the tentative plan and schedule of the course will be this introduction is over. We will be, we are on time with this. And next we start talking about neural networks, and we begin with a neuron, with a single neuron. I'll show you architecture, function, training, and hopefully we'll be done with this single neuron in 2 hours. And then we will get to a little bit more complex stuff. We'll be combining these neurons and building networks. And finally, I will just indicate you what are deep neural networks, because all these functionalities that made neural networks competitive to humans, they come from this deep learning paradigms and deep neural networks. So I will just indicate what is more or less what is this deep learning. And I might also cover some other selected topics related to neural networks. And then we move to the second concept. We'll be talking about search algorithms. And finally, we conclude with fuzzy logic basics. So that concludes introduction. And please stay with me because we have still 1 hour. Do you have any questions maybe related to the organization of the of this course, or do you have any? Okay. Okay, if you, some of you possibly got no email from Mr. Piotr Łuczak, and thank you for this response. I would ask everyone who received this letter and who got such a request to forward this letter to your colleagues, because not all of them were known. Not all of email addresses were known to Mr. Łuczak. Okay, now I would like to switch to another presentation. And the only problem is that I don't know how to do that. Okay, I'll try to get to resources. Okay. Nope. So give me 3 minutes. And what I can do is I can only share the file. And now I'm trying to okay. So okay, so let's begin talking about neural networks. We'll be talking about artificial neural networks according to the schedule that I have just presented. And what I'd like to begin with is that people realize that artificial intelligence is tough, is hard, just because it was not that easy to solve several tasks that involve interaction with the real world. Where we are confronted with real world, then the rules are no longer that simple, and they cannot be easily packed into a set of different reasonings that can enable us solving problems. So for example, we have a sample recognition task. So what can you see here is a picture made of black and white blobs, and the question is, what is on this picture? And I wonder whether you could try to answer me whether you can see any sense in this picture. If it is possible to, could you try to understand what is in this scene? Superb. Yeah, it's very good. Dalmatian dog that is sniffing grass, and there might be a tree there, and so this Dalmatian dog is basically somewhere here. Here is this Dalmatian dog. And if you think on how this problem has been solved, you conclude that it is unlikely that it has been solved using any rigorous reasoning. The essence of our ability to recognize things lies in our experience rather than in logical deductions that we are doing using some input data. So it is common to many different activities that we are very good at. So we are good at recognizing images of this kind. We are good at recognizing speech. If you would like to see how double quotes see the speech, you will notice that the same word uttered by the same person never looks the same. Yet we are able to understand it. So there are many tasks that cannot be solved in any simple or even complex algorithmic way. Many tasks need to be solved in a different way. And that was one of the motivations for launching research on neural networks. because computers in 70s, 80s, 90s were unable to communicate with us using speech, for example, just because we were we had no good ideas on how to algorithmically help computers to understand speech. So people decided to try to copy or clone or emulate the way we are doing that. And that was one of the incentives for developing research on neural networks. And that was the goal. The goal was to try to understand biology, physiology, the way of operation of our nervous systems, hoping that if we will get it, we will be able to build algorithms or devices, because maybe we will try ultimately to implement all these artificial neurons in hardware. We'll be able to build intelligent machines, or machines that are no less smart than us, than ourselves. Actually, if you think about our nervous systems, and if you learn a little bit more about our nervous system, you will see that it is not an objective tool for processing information. So the task that is being solved by our neural networks is very often biased, and with our experience, it is often biased with the fact that we are using living cells that get tired, that burn out of energy, and results of operation is very often erroneous. So we will be trying to build devices, machines, algorithms that are better than us, that do not have these limitations. And please forgive me, because the next slide I will show you later on, not now, because now it is impossible to get the point, because I didn't prepare it correctly. So later on we'll be back to that. We'll be talking about neural networks and the basis. The basic element component is a neuron, and the neuron is a cell, is a living cell. We can look at this cell from different perspectives. So we can look at this cell from a perspective of trying to understand each detail of its operation. And this is a very rich source of problems that are fundamental and that can possibly result in extremely revolutionary findings. And these solutions can bring you Nobel Prizes. This is one aspect of studying neural networks. And I'm just showing you this slide because we will not be dealing with that perspective, because this perspective is not really very important from the point of view of understanding operation of a nervous system from this functional point of view. We are interested in a functional aspect of operation of nervous system. We are not going in artificial neural networks to provide algorithms that emulate accurately all the processes that are taking place in nerves. This is something that we are not really interested in. What we are interested in a functional description, and this functional description is something that doesn't really care for all these details of processes that take place in neurons. So this is a slide just to show you that the first thing, there is a lot of research that has been made. The second thing, people got Nobel Prizes for this research. There are more Nobel Prizes for studying neurons than that. There are 3 Nobel Prizes for studies on a neuron. And the third purpose is that, as you see, that these are some electric models using electric components, models of a neuron, because neurons are basically processing charged particles, ions. They can be seen as wirings in our organisms, and that some currents or some chunks of ions, they flow through neurons from one neuron to the other neuron. So this is something that we will be just making use of. That neurons are cells that manipulate charge. They manipulate ions. They pass ions to the other neurons. They receive ions. So these are electrical interactions between these units. So basically, I will try to scribble a little bit, and later on you will see the slides that have a little bit more decent versions of what I'm going to draw here. But basically, what is a neuron? A neuron is a living cell. So this living cell, I'm not very maybe good at. I'm not good at all in drawing, but basically the neuron looks a little bit like that, where it has some inputs. I'm talking about a functional point of view. So I will make an output in a different color. So a neuron is a cell, and this is a cell that has several terminals, input terminals and one output terminal. So these input terminals are terminals where other neurons are connected, and these neurons, they generate spikes, electrical pulses. So these pulses are fed to the input terminal of this orange neuron, and this orange neuron is monitoring many activity of many other units. So here is some other unit that is producing spikes at different rate. Here is yet another neuron that produces spikes at much higher rate. Here might be another neuron that is producing spikes at a lower rate, and so forth. And what neuron does, this is so these are input terminals for a neuron. Input terminals, and in biology they are called dendrites. So dendrites are inputs to the neuron. So this is E. And this, what enters this orange neuron are every pulse is a packet of a charge, or is a packet of ions. So these ions, they flow, and here in this cell body, because this is a cell body or neuron's body, they accumulate. And if there are, if a potential of a cell body exceeds a certain threshold, because we are accumulating a charge, so we can accumulate up to a certain threshold, and if this threshold is exceeded, a neuron will fire or will generate a pulse, and it will send it to some other neurons that might be interested in communicating with this unit. So it is a very, very coarse picture of what happens in a neuron. But basically, what happens is that I have this small little charged particles. So let's say these are positive or negative. So every dot is a particle, is a charged particle. So I am applying these particles to terminals. And one thing that is very important for neurons is that there is at every input, what we have is we have a structure that is called a synapse. A synapse is an electrochemical mechanism, or it contains. It's a kind of a device that is using some complex electrochemical mechanism, and this mechanism is modifying influence of the input on the cell body. What does it mean? This means that if I can imagine a single input, at this single input, I'm applying electrical pulses to this single input. So I am applying this to a single input. That means that I am, let's say, applying ions. Let's say 3 ions. Let's say they are positive. So this gets applied to input terminal, to a dendrite. So let's say that I have 3 pluses flowing to the right. And now there is this synapse, and this synapse is a structure that can do a few different things. So what are these things? The first thing is that it can proportionally reduce or increase number of positive ions that flow to the right. So for example, it can kind of amplify this. So instead of 3, there will be here will be 5. Or it can reduce number of ions. So instead of 3, there will be 1. And the second thing that it can do, so this is amplification and this is reduction. But what can also happen is that it can drain positive charge from a cell body. So it can either pass these positive ions in a different amount to the cell body, or it can take away these positive ions, or alternatively insert negative ions. So we have 2 different kinds of synapses. The synapses that operate according to this scheme are called excitatory synapses. And synapses that operate according to this scheme are called inhibitory synapses. And what we are interested in AI and in artificial neural networks is how to make a simple model of the process that is taking place in a neuron, in this living neural or nervous cell. So the first thing is we will be trying to simplify everything. The first simplification comes from the realization that if we would like to make a model or an algorithm that is dealing with pulse-based representation of information, that this algorithm will be complex, will be difficult to get analyzed. So we have 2 different possible activities. So let's say that this is a time axis, And here on the vertical axis, we have some voltages. So we have voltage versus time. So this representation is not very convenient for, it is no simple at all. But so here is time. But it turns out that information that is being passed between neurons is encoded in this rate, in a rate of firing. Information means that the number of charge, the amount of charge that I'm passing to a neuron. The more active is neuron, if it generates more spikes per time unit, I'm saying this is more active. If it generates less spikes or less pulses, I'm saying it is less active. A neuron can be completely inactive. So a neuron can generate no spikes at all. So this will be inactive neuron. The neuron is a living cell, so it cannot fire at arbitrary high rate. So there will be some maximum possible rate of firing for a neuron, just because everything in physical world requires some time. So a neuron is firing very frequently if it gets a lot of charge from the outside and has this excitatory synapses, but still it needs some time before its potential exceeds this threshold value. So information in neuron is embedded or encoded by a rate of this firing. Basically, this is the information that every neuron gets. What is the rate? So if this is the case, the first simplification that is being made in neural networks is to convert rate into real numbers. Real numbers. So that's something that tremendously simplifies analysis. So instead of trying to emulate a neuron that is having at its inputs, so this is, let's say, this neuron, having all the trains of pulses at different rates, I will be just assigning real numbers to the input. So here I will tell, okay, this is my input x1, and at this input x1, I will have a particular value that encodes activity of a neuron that is attached to this input. As neurons can change rate from being inactive to some maximum value, it is customary to assume that a range of these numbers comes from some interval. As the neuron can be inactive, that means it is a zero activity. Frequently, a lower bound of this range is 0, and the maximum range, just to make it clear and simple, is 1. This is one of the most frequently used encodings of activity of incoming signals or activity of incoming information. So a neuron can get a real number at its input. So let's say that I can say that at this particular time instance, that this neuron gets 0.5. And this neuron here is input number 2, is, let's say, 0.3. And maybe this neuron here is inactive, so it gets x3 equals 0. And it will produce some value of y. So this is the first step of simplification. We can say that a neuron, from the point of view of schematic diagram, could be a device that has many inputs, from x1 through x2 up to xn. And at these inputs, we will be having numbers. These numbers will be applied to a neuron. What happens next are these synapses. So what is this synapse? This synapse was a modifier. If I'm trying to modify a value of x, I can say I can make it in an abstract way by introducing some constant coefficient. And so I can say, okay, I can apply a constant coefficient that I will name W1, and a result of its operation will be to multiply x1 by W1. So I'm doing weighting, and this coefficient is called the weight or weighting factor, but it's just typically called a weight. And the same happens for every neuron, because every neuron is connected to its inputs via this synapse. So there will be some W2. So we have a product W2X2. And here we will have a weight Wn, and we'll have a product Wn times Xn. So my model right now, what it accounts for is for this initial phase of inserting information to a neuron. We have data, input data, and this input data corresponds to activity of neurons that feed the unit that I'm interested in with information. So these x1, x2 through xn are just real numbers from this interval, for example, from this limited interval. Now I have weighting factors. These weighting factors can be positive. If they are positive, that means that I will have excitatory synapse. And if this value is negative, then I will have an inhibitory synapse. So this is a very good modeling, very accurate modeling of the processes, of these complex processes that take place in a real cell. So what happens next? All these contributions are then being accumulated in a cell body. Accumulation is just summing of charge. But this is a weighted charge, because now I have a charge. This x1 represents, is a real value that corresponds to the amount of charge that has been delivered, but modified using a weight factor. So basically here in this place, this is a cell body. What I'm computing something that I called activation of a neuron, or it is more commonly used term a state of a neuron. I will be computing a state of a neuron, and the state of a neuron is just a sum of all of these components. So far I can say that what I'm doing is I'm computing a state, and this state is just a sum of products. So this is what I'm computing in the cell body, up to Wn, Xn. Obviously, I can make it more compact. So I can say that this is just a sum of products from the first input till the last input. So I'm computing a state. So my neuron looks like, I will rewrite it or redraw it. So this is my neuron. I'll just draw the first and the last input. So this is xy1, xn, and here is this summing operation, and here I have a state. Actually, I'm using this notation, but this is not the favorite notation that is used in the realm of neural networks, because basically what I can say is that I can arrange the input data into a vector. So I can say, okay, I have a vector, and this vector contains as many components, as many inputs my neuron has. And similarly, I can say I can arrange back all these weights into a weight vector. So I'll be having a weight vector that is composed again of n components, and these components correspond to these properties of synapses. And I can say that this, what this information, what this operation is, this operation is a simple dot product of these two vectors. If I underscore something, I will be trying to emphasize that this is a vector. I will be trying to be consistent. Sometimes if I forget, please let me know. So we are partly done with modeling a neuron. A neuron is a device that accumulates input data, accumulates, to be more specific, it accumulates a weighted sum of input data. But what happens next? At the end of a neuron, what I should produce a value that is feasible from the point of my assumptions. My assumptions were I would like all the signals or the data in my structure to belong to this interval from 0 through 1, for example. So y is expected to belong to this interval. Now, as you see at this expression here, it can be a real number that's of arbitrary magnitude. There is no any mechanism here that prevents us from going out of this range. And this neuron will be an element of a network. So all neurons should be the same. It will be feeding some other neurons with its output signals. So it also should generate only values from this range from 0 through 1. So what we need here? We need here a function that is converting the state onto output, and it converts it so that a range of this function will be limited within this belt from 0 through 1. So this will be a function that I will name f sub s, and this f sub s will be called activation function, or neurons activation function. And here there are many ideas on what activation function could be used. So let's begin with the simplest one. The simplest one is the function that is trying to squeeze this range of potential neurons states into this output range, and is trying to, I will use a different color, let's make it green, according to the simplest possible concept of a step function. Step function, sometimes this is called a Heaviside function. So this step function, or a Heaviside function, is a function that that is very simple. It is a step function. This step function has its transition period or transition point at some threshold theta. This theta is a threshold value. And if you recall, I told you that the cell body, the neuron's body, can accommodate some amount of of charge, of ions, until some threshold is being exceeded. And this is the threshold. So this threshold, if it gets exceeded, my neuron will tell 1. If my threshold is not exceeded, my neuron says 0. So if we adopt this function, we get a binary neuron. We get a neuron which can have only one of two different output values, either 0, and this is 0 if my activation is below my threshold, or 1 if this is, for example, greater or equal my threshold. And this neuron with a step function or step activation function has a very fancy name, because it has a name. Its name is perceptron. So we have perceptron. Perceptron is a neuron with a nonlinear step activation function. So let's move on. So what I told you so far is that a neuron is a computational unit that basically is computing a nonlinear transformation of the expression W transposed X minus theta. So that's this function. This is the function. This is S, this is Y, and if this is a Heaviside function, it has this particular parameters or shape. A drawback of this perceptron is obvious. We can have only neurons that are inactive or maximally active. This is not a good way of modeling real networks. The intensities, all the range of activations is something crucial to operation of a real neural network. If so, it is good to think what other activation functions could be used here. The constraints on an activation function are very mild. What we need is a squeezing function. That's the first requirement. The function should squeeze a range of real numbers, because state is a real number, into a finite interval from 0 to 1, for example. So this is the first assumption or first requirement. We need a squeezing function. The second requirement is that it should be monotonous. And basically, any function that is satisfying these two requirements is suitable. I'm having some feedback, so just I apologize. I need to. The option would be mapping. I'm not quite clear on that, so maybe later we could discuss this point, the question that has been posted on the chat. So I'm going to continue. So we have two requirements. The first requirement is that it needs to squeeze a dynamic range. The second, it needs to be monotonous. And any function that satisfies these two requirements could be used as this output neuron activation function. And obviously, there are some functions that are being used and preferred with respect to the others. So a general shape of the function that I'm talking about is, for example, like this. So this function looks like an elongated S-shaped transformation. And that's why a general name for this kind of a function is called a sigmoid, as it resembles a character S. And there are many sigmoid functions, and one of the functions that used to be a favorite activation function for a neuron is a logistic function. Logistic function. And logistic function is a function that transforms my state according to this. This is the simplest form, according to this expression. As I said, this is the simplest form of this function. We have still here this theta. So I can say, okay, this is S minus theta. And we can easily check whether this is a function that satisfies our requirements. The first, whether it really squeezes the range. Now, you can see that if S goes to minus infinity, S goes to minus infinity, then e to the power of minus times minus infinity means e to the power of plus infinity makes an infinity in denominator. So a value of the function goes to 0. So y goes to 0 if S goes to minus infinity. If S goes to plus infinity, then e to the minus infinity is 0. So y goes to 1. And if S equals theta, then we have 1 over 2. So y equals 1 over 2. So this is a valid candidate. And obviously, I could also compute a derivative so that I can show you that it is monotonous. But I'm not going to waste time because you can do it on your own. So the sigmoid function is, as I said, it used to be the favorite nonlinearity that was being considered for neurons. It was not the only one. We had a whole bunch of different nonlinear functions that were considered for neurons. So the functions that were also considered, for example, were so-called radial basis functions. So RBF, that means radial basis. It was a function that was maximum at the beginning, at the origin, and it dropped to 0, both positive and negative way. What happens right now is that we are not really using sigmoids that often. And the most commonly used function for deep neural networks is something that is called rectified linear unit. So this is the nonlinearity. Observe that this function is not modeling a physical behavior of a neuron. Why this function has been adopted, I will tell you a little bit later, as the one that is most frequently used right now for neural networks. Anyway, we have many candidates that are biologically plausible, like the sigmoid, for example. One of the variants of a sigmoid is a function that has this sigmoid shape like this, but is bipolar, because for now we were talking about unipolar functions. That means functions that map state to a unipolar value from 0 through 1. This sigmoid function is something that is mapping state into output that belongs here to a bipolar range. And here the function that is commonly used is a hyperbolic tangent. So I can say that this is also one of the frequently used solutions. And again, in case of this hyperbolic tangent, this is also infeasible biologically. So among biologically infeasible solutions are, for example, this ReLU or this hyperbolic tangent. In terms of biologically plausible solutions, what we have is this logistic function, and basically, this is what I wanted to tell you about this output nonlinearity. And before I proceed, I will just make one more modification of a description of my neuron. So my neuron is described right now as an operation, mathematical operation, that transforms a dot product of its inputs and weights onto a scalar value. If I would like to identify what are the inputs and what are parameters in this equation, I can say that obviously input is x, and all the remaining elements, means this and this, are parameters. So these are parameters of a neuron. And so these are parameters of a neuron. The expression that I have wrote could be simplified. How can we simplify this expression? What I can say is, I can tell that as theta is also a parameter, I can introduce kind of an extended, let's say, w hat vector. And this w hat vector could contain, in addition to all the weights that previously were packed into this vector, let's put at the first place, at the first position, this parameter theta here. If I introduce an expanded vector of inputs, I can tell I can define such an expanded vector by using all n inputs that I used previously, but also I can put one extra element at the first position, and this element is -1. So observe that now if I compute a dot product between these two vectors, then what I get, and dot product is just a sum. Now it starts from 0 through n. It's just a sum of products of corresponding entries. So this sum of product of corresponding entries, I can obviously here convert into a sum that contains n elements, and the last product, or the first product, is -1 times theta, which is what we had before. So this was my original argument or original value of a state. So to make description of a neuron as simple as it is possible, it is customary to use this notation and define a neuron as a device that just transforms a dot product of inputs and weights onto the output. And here I'm skipping these hats because this will be a notation that we'll be using from now on, at least for a while. So just to conclude, we have a neuron, and the neuron is a device, a computational device that is transforming inputs to an output value. So it transforms a vector into the output scalar. And I'm sorry, I guess my time is over. So let's probably put a period here. I defined a neuron and I used a model for that neuron that has many inputs. It has many weights, but each weight is assigned to an input that computes a weighted sum of these inputs that converts it according to a nonlinear transformation and produces the output. So this is a block diagram on the right of a neuron. On the left, what we have a mathematical description of neuron's operation. So we have a computational device that can be modeled using a simple algorithm, because basically what I have here, this formula, can be translated into a simple algorithm. And it gives us a neuron. And what is interpretation of its neuron operation and how to make this neuron useful? We'll try to clarify a week from now. So I'm turning off